This is Mrs. O'Neill for AP Chemistry, Chapter 5, Section 5, Calorimetry. The objective for this section is to examine calorimetry, which is just an experimental technique used to measure heat energy changes in chemical reactions. Again, I suggest to pause, fill in the blanks, and then play to hear my words. Remember that delta H is enthalpy, and that's heat energy. And remember, that has to be determined experimentally, because we can't measure the change in energy internally of the system. We actually have to measure the surroundings. We feel the heat or we feel the warmth, and then we do the equals negative Q. Remember that. So calorimetry just measures that heat flow. So when a reaction is exothermic, the thermometer will go up in temperature because that's the surroundings, and we will measure that the heat went from the system to the surroundings. If the heat flows from the surroundings to the system, then again we know that it was an endothermic reaction. So a calorimeter is just that device or that tool to measure that flow of heat. So heat capacity is the amount of heat needed to increase the temperature of an object 1 degree Celsius. And it's labeled as C, or that's the symbol. The units are kilojoules per degree Celsius. And it's going to depend on the mass and the chemical composition of that substance. So we want to remember that this is considered molar heat capacity. So heat capacity is per mole. So heat capacity is similar to specific heat, which you learned probably in Chem 1. So specific heat is the amount of heat needed to raise 1 gram of substance 1 degree Celsius. So again, it also has a symbol of capital C, and its units is joules per gram degree Celsius. So what's the difference between heat capacity and specific heat? Hopefully you took notice to the units. One's in kilojoules per degree Celsius, and one is in joules per gram degree Celsius. So it's dependent on the mass. So read this over and see if you can answer the question. Hopefully you guessed mercury. So again, rearranging the equation gets T, gets your constant divided by that specific heat or that heat capacity. Therefore, the element with the smallest specific heat has the largest delta T. So I'm going to go back there and show that to you again. Again, read this over, look at the information that's given to you, pause if you need to, and make sure that you understand that it is mercury. So in a constant pressure calorimetry, probably very similar to one that you might have used in Chem 1, and we might do a reaction or a lab in this chapter as well. So this is going to be your calorimeter, and it's called a styrofoam calorimeter. So styrofoam is very, very heat resistant. So it contains the heat when there's a change. So here's our stirring rod to make sure that everything is stirred up. So when we're measuring with the thermometer, it measures pretty accurately. So this is what they call a coffee cup, because we're using a styrofoam calorimetry. Again, usually used for exothermic reactions because that would be heat lost by the system, but then it's gained by the surroundings. Then in this case, it's water. So you're really making a solution, and here's that Q equals negative Q. So remember that they are opposite of each other. This is on your reference sheet, Q equals MC delta T. So I wanted to make sure that we understand this equation. M is the grams or the mass of the solution times the specific heat of that solution. In this case, most of the time you're going to use water, 4.18, and then of course the change in temperature. Okay, so again, for dilute solutions, it says to use the specific heat of water, which that's what we'll be using in lab. So a bomb calorimeter is very similar, but instead of a styrofoam cup, it actually is like a metal container. And inside, you actually have your sample. So let's say you have your sample of M&Ms, okay? This is where they get calories from. So they're going to put 1 gram of M&Ms in there. They're going to hook it to some wires and basically burn it. They're going to zap it and burn it. And then this stirring rod is going to stir the water, and you're going to see the temperature rise. So that temperature increase is going to tell us how much heat was lost to the surroundings from those M&Ms. So for M&Ms, that temperature is probably going to be pretty high. or that temperature change is going to be pretty high. But if we put a carrot in there, let's say, so if we put a little piece of carrot in here and zap it and burn it, 1 gram of it, the temperature change probably wouldn't go up that high. So that's where the calories come from. So the more heat that's released, the more energy it's going to need to be used in your body to burn it off. So that's why something like M&Ms is going to have a high temperature increase, where a piece of carrot would have a low temperature increase. Okay, so studies, this bomb calorimetry really is used to study combustion reactions or burning reactions. So you can read over these steps. Again, this is something that if you do see, again, it will be in your college level classes. We do not have bomb calorimeters, but I did use one in college, which was pretty interesting. Okay, see you in class.